So we have an example for the fan, and in this example we are going to find the power of the fan and as well as its some other properties. The example statement is as we have the room with a dimension of 7 meters, 3 meters, and 3 meters. This is the volume of the room. Okay, and overall it makes 9 into 7, 63 meters to the power of 3. And there is a fan that is supplying a velocity of 10 meters per second. And overall efficiency of the fan is 55%. We have the overall efficiency as 55% or 0.55. And the question says that determine the power of the fan, the pressure difference across the fan between, for example, these 2 points, and the diameter of the fan casing. So what diameter of the fan are we going to use? D. It is required to replace the air of the room in 10 minutes. Okay, so it says that the time required to replace is 10 minutes or 600 seconds. Environment pressure and the temperature is 1 atm and 25 degrees Celsius respectively. Okay, so to solve the example of the fan, we are going to use the famous concept, which is the actuator disk theory or the concept here. So what is the actuator disk theory or concept? In this concept, you are replacing this device here with a disk. Okay, but this disk is an actuator because it changes the values of the fluid. Okay, and away from the, so this, let's say that this is the point 2, very close to the disk, and the 3 it is at the back of the disk. And you have taken some point here, which is 1, and another point here, which is 4. And between 1 and the 2, we say that here, so it is ideal fluid, and also here it's also ideal. Okay, so we are considering ideal fluids, and as well as these 2 and the 3 points, you are also considering the ideal fluid here. Okay, 2 and the 3 here, you also ideal fluid. And another thing here is that between 1 and the 2, we are saying that the work of the disk or the actuator here doesn't affect the flow. Here, say that the work input, okay, doesn't affect the flow. It goes in an ideal fluid, and here also it goes in an ideal fluid. The work input from this one okay. And then let's see how the pressure and the velocity change very close to the fan as well as away from the fan. Okay, and since it is ideal fluid, we can write the Bernoulli's equation, which says that the P plus rho v squared by 2 plus the rho gz term, that is equal to constant. And for the air problems or any gas problem, this rho gz term is approximately 0. It is not important. So for gases, in our case it is air, therefore no problem. But even if so this is the general case, but for this problem, what you can do is that you can take the 1 and the 2 and the 3 and the 4 at the same height. Okay, since you have taken them at the same height, again, this term doesn't come into picture. But generally for air and the gases, we don't consider the rho gz term because rho is very small. And now let's look at the profile change, the change of the properties or their profile near the fan, near the disk, and away from the disk. So this one is the pressure profile, and this one is the velocity profile. Okay, and this one is 0.1. This one is very away from the fan. Okay, it is away from the fan, very far away from the fan, and this is also the 0.1. At the 0.1, you have the PATM, atmospheric pressure. Since it is far away from the fan, it doesn't affect the flow, Therefore, the pressure is 1 atm. And here, the velocity at point 1 is 0 meters per second. Okay, therefore, this one is 1 atm and this one is 0 meters per second. And as you close to the fan, the velocity increases because fan imparts work on the fluid here, the velocity increases. But we know the Bernoulli's principle says that P plus rho v squared by 2 should be constant. Add it, P plus rho v squared by 2 should be constant. So therefore, since this one increases, that one should drop. You can see the points. Since this one increases, that one should drop until the point 2. Okay, it is the point 2 here. And the 2 is very in front of the fan or in front of the disk here. It is the point 2. And then comes point 3 at the back of the disk or the fan. You have a discontinuous rise from pressure 2 and to pressure 3. Okay, this one is the discontinuous. This is the concept, okay, the actuator disk theory, what it says. But the velocity is always continuous. Okay, we don't consider the velocity as discontinuous, and it is always continuous. So therefore, from 2 and 3, the velocity value will be approximately here. Okay, from 2 and 3. Then the pressure again drops to P atm here, which is the 0.4. Like it. Then the 0.4 comes. This one is the P atm again. You have dropped the pressure value to P atm. This 2 and 3 part, it is due to fan power. And this pressure increase, as always, is converted into this part. Okay, converted into kinetic energy or the increase of velocity. Similarly here, this part, it is converted into kinetic energy. Okay, then you have reached the point 4, and at the point 4 you will have the 1 atm, but all of the pressure has been converted into kinetic energy with a velocity of the 10 meters per second, which is the maximum velocity that you will get from this equation, from this problem, 10 meters per second. Okay, this is the pressure profile and this is the velocity profile. Now comes the last profile, which is the sum of this, P plus rho v squared by 2, which is the constant term, and the till point 2, from 1 to 2, this 2 is constant because we don't have any work here. This is 1, this 1 and the 2 is constant, and from 2 and the 3, this P plus rho v squared by 2 changes. Okay, changes, it is again increases, it is due to fan. Fan adds work into this energy. This one, the P plus rho v squared by 2. This is the energy of the fluid. But when you reach from 2 and 3, the energy of the fluid will increase due to work of the fan. The work of the fan will add some more energy to this sum here, total here. That total will increase to the point 3. And then from 3 to 4, this will be again constant. It will not change because there is no any work producing device or work consuming device. Okay, so we have, this is the profile that we'll see. Now let's solve the question one by one. Firstly, it says that to find the power of the fan. Okay, to find the power of the fan, we will write the energy equation between 1 and 4, because here in this case, if you take the 1, it means 1 atm, velocity is 0, and if you take 4, 1 atm, and you know the value of the velocity. Therefore, between 1 and 4, the number of unknowns is less, therefore we can solve the problem with taking these 2 points. So let's write the energy equation. So I will write, as I've said, I've wrote energy equation between point 1. So these are the point 1 and this is the point 2. Similarly here, this is the point 2, and then 3, and then 4. Okay, so I'll write the energy equation between 1 and 4. Let me write it so that you will have the m dot multiplied with the P1 by rho plus V1 squared by 2 plus GZ1 plus the fan power, which is the work dot fan, and this power will be useful one. We are not considering the losses here. And then you will have the m dot multiplied with the P2 by rho plus V2 squared by 2 plus GZ and 2. For the air problems, we have said that you will have here in this case it is not the 2, it should be 4, because you are writing between 1 and the 4. Okay, therefore GZ4. And between 1 and the 4, you can take the point such that, say that this is point 1 and this is point 2, but instead of the fan you will have the disk. This one should be disk, not the fan. Point 2 and the point 3 and the point 4. You can take 1 and the 4 such that they are at the same line, same horizontal line, or even if you can't do that, so if the streamlines are not as you want, in gases we have said that we are not considering the rho GZ term. Okay? Therefore, the term that's here, which is GZ1, cancels out. And because the Z1 and the Z4, they are the same. For the velocity terms, velocity at 1 is 0 meters per second, because it is far away from the fan, therefore here you don't have any velocity. And the velocity at the point 4 is the maximum velocity, which is 10 meters per second. Okay. And then we'll have this term goes to 0. P1, pressure 1 atm, so this one is 1 atm, and here you also have the 1 atm. And here it is 10 meters per second, and here it is 0. And therefore P1 is the same as P4, it is 1 atm. Okay. These are also away from the fan, where you have reached the 1 atm pressure. Okay. These two terms cancel out, and then you will have only the left hand side goes away, this term is not there. You will have the work fan, which is its power, will be equal to that m dot multiplied with V4 squared by 2. It is just the kinetic energy of the air at point 4 with the velocity of 10 meters per second. Only unknown here is that m dot, which is mass flow rate, is equal to rho v dot, and the rho is the density of the air. It is at 1 atm to 25 degrees Celsius. Okay. And use ideal gas relation to find the 1 atm. It is 101, 326 pascals, and 25 degrees Celsius. You can reuse the ideal gas relation to find the density here, and you will get 1 point that it is 18 kilograms per meter cube, or you can take approximately this one is 1.2 kilograms per meter cube. And the V dot value, this one will be equal to, the question says that the volume of the room is 733. Okay, this one is the volume of the room, which is 63 meters cube, and says that it is replaced in 10 minutes. So time for that is 10 minutes or 600 seconds. And therefore, the volume change of the room per unit time, okay, that will be equal to V dot. And that V dot term will be equal to 63 divided by 600 seconds. That will be V dot term, let's write it here, 63 divided by 600 seconds. Okay, so you have the m dot value, and you have the V4 squared by 2 value, and if you calculate the result of this one, you will get the power of the fan, which will be equal to 6.216 watts. That will be the power of the fan. It is a useful power, okay, I should add it, useful. But if you are looking for the real one, work that real, you should consider the efficiency of it, which will be work that useful divided by its efficiency. It is 6.216 divided by the efficiency is given in the question as 55%, or divided by 0.55, and you will get the real power of the fan, which is equal to 11.3 watts. A small fan power. Okay, a small fan power will be enough to replace the air of the room in 10 minutes. Okay, so now comes the next part of the question. It says that find the pressure difference across the fan. In other words, find the difference between 2 and 3, which is discontinuous here. And let's do that. Also here, and the 3 is here. This one is continuous, therefore 2 and 3 cannot be at the same point. Let's do the second part. Okay, therefore we will write the energy equation between 2 and 3. Okay, let's write it. So that m dot multiplied with P by rho, And by the way, for the first question, so this one should be m.1 and this one should be m.4. But since m.1 and m.4, they are the same, therefore you don't consider the 1 and the 4 differently. Okay, for the m dot multiplied with the p1 by p by rho, this is between 2 and 3. p2 by rho plus rho v2 squared by 2 plus rho g and z2 plus fan useful. This one will be equal to m dot 3 multiplied with p3 divided by rho plus rho v3 squared by 2 plus rho gz3. And we have said it, the potential energy change is not important. Even if it is important for this one, we can take the points that are at the same line. Therefore, it will be at the same height. And the rho v2 and the rho v3 terms, now let's go back to the chart here. You can see that the rho v2 and the rho v3 doesn't change too much. Okay, so, but if you go from that one to this one, it changes, it goes from 0 to 10. But between 2 and the 3, there is not enough change. Okay, the fan increases pressure. You can see it here. The fan increases pressure, but it doesn't increase velocity too much. Then the pressure increases, the pressure drops into a kinetic energy. But for the fan, the kinetic energy is not so important. The pressure difference is important, and it increases the pressure. Okay, therefore the V2 and the V3, it is approximately the same. These two terms cancel out. And the P2 and the P3, the question asks for the difference between them. So therefore I can write that work dot fan useful will be equal to m.2 is the same as m.3. We can add the subscript here, they are the same, and it will be m dot multiplied with p3 minus p2, and that one divided by the rho. Okay, and the question asks what's p3 minus p2, and if you calculate it, that will be delta p, and the value will be 107.6 Pascal. That's for the pressure difference. So we have done the second part of the question, first part of the question. Now comes to find the diameter of the fan casing. So which diameter for the fan are we going to use? Let's write the last part, which is the third part. Here you have the fan. Okay, see that this is the fan that we are going to use. The fan will operate in a circle. It will be circular. And for this circular fan, you will have the mass flow rate into the system. Okay, that mass flow rate m dot will be equal to rho and the cross-sectional area of the fan multiplied with the velocity. We'll go back to here. You will have some cross-sectional area here. That cross-sectional area will provide for the mass flow rate here. M dot will go through that cross-sectional area for the fan. Okay. And the rho value is okay. We know it. It is 1.2. And the AC value, it is pi diameter squared by 4. And the diameter is this one. If this is the center, we'll have the diameter value. Similarly here, we will have the diameter value, which is the diameter here. And then you will have the velocity value, which is 10 meters per second. If you do this calculation, you will get the diameter of the fan casing as 0.12. But you can also get the simpler approach. Simpler approach is that the density doesn't change. Okay, it will be incompressible. Therefore, V dot will be constant. Okay, if V dot is constant, that will be equal to area into the velocity. And the V dot is given in the question. That is the 63 by 600. Okay. And this step, you will get the same result. It doesn't change anything. but at the end it is okay. Velocity is 10, and you will get the same result, which is 12 centimeters or 0.12 meters. That is the end of the example. So we have done the example by the concept of the actuator disk.